Welcome everybody. Today we are going to be talking about the convolutional neural network. This is a very exciting part of neural network, and it's a very exciting part of deep learning and AI. So we're going to talk about those concepts a little bit as well. Once again, this is presented by EDU Ionics. I hope it can help you gain an understanding of these networks, how they work, and what they can do. All right, so let's get started. What is a convolutional neural network? Well, a convolutional neural network uses local connectivity and shared weights to produce a layer of learnable filters. So if you're at all like me, when you first heard this, you probably had no idea what local connectivity, shared weights, or learnable filters are. So that definition doesn't really help, but fortunately, we are going to explain each of these in turn throughout this video. So first, convolutional neural networks are designed to work on images. So they have an input assumption of images, and this allows us to encode properties into the architecture. These properties being the local connectivity, shared weights. So here was our previous neural network, simple 3-layer network. It's got 2 hidden layers and an output. A neural network, a convolutional neural network, is going to look a little bit like this. So one of the biggest and most obvious differences is right away that the CNN or ConvNet has depth. So the layers of a CNN or convolutional neural network have neurons arranged in 3 dimensions: width, height, and depth. Every single layer of a convolutional neural network transforms the 3D input volume to a 3D output volume of neuron activations. So huge difference there. And this is kind of that architecture that is designed to work with images. So if we had an image of the size 200 pixels by 200 pixels by 3, because we have a depth of 3, because we have a color image, this would lead to neurons that have 200 by 200 by 3, which is 120,000 weights. And so we would almost certainly want to have several such neurons, so the parameters would add up very quickly. This would be computationally extensive and could lead to overfitting quickly. And as a result, we're going to employ the local connectivity and shared weights to alleviate those issues. If you look at the image here on the right, you see that we have a volume to that original input, our pink layer. That volume is going to be the depth of 3 for the color of the image. And then we're going to successively transform that volume into our final output, which is going to be a classification. Typically for images, we're dealing with classification. In fact, you're never really going to do regression on an image. That one makes sense. So our output is going to be a vector row of however many classes that we have. So let's keep going and talk about these concepts of local connectivity and shared weights. So local connectivity is simply the fact that each hidden unit is going to be connected to only a small patch of units in the layer below. Local connectivity makes each unit responsible for extracting local features from the layer below and reduces the total number of weights considerably. So when we say local features or features in general, we might be talking about properties of the image, such as maybe a blotch of color or an edge or contour. So these are the features that we're trying to extract, and in those hidden layers, those are going to be called feature maps. And so we'll keep learning about what those features are, but the features are what are extracted by what we're calling a learnable filter. And the learnable filter really comes from the fact that each individual node or unit in the hidden layer is only going to be connected to a small volume. We also have shared weights. So in shared weights, all the units in a local feature map perform the same operation on different parts of the image by sharing the same weights. And this is what that would look like a little bit. So we're going to see in some later representations that we are actually going to maintain the same weights and then slide these different features, or well, not these features, we're going to slide these different filters over the entirety of the image to produce our final output. So local connectivity and shared weights. Local connectivity, simply we're not connected to every single input. We're only connected to a few of them. And then the shared weights, we're going to maintain our weights so that we can extract the same features from different parts of the image. And that is going to result in learnable filters. So each filter is going to be small spatially, but it is going to extend through the full depth of the input volume. So for example, a filter in the first layer of a convolutional neural network might have the size 5 pixels by 5 pixels by a depth of 3 for all 3 color channels. And this is going to kind of be that concept of local connectivity. With a 5 by 5 filter, we're only going to be connected to those 25 pixels, or 75 if we have a depth of 3. During the forward pass, we're going to slide, or mathematically, this is called convolution or convolve, each filter across the width and height of the input volume and compute the dot products between the entries of the filter and the input at any position. As we slide the filter over the width and the height of the input volume, we will produce a two-dimensional activation map that gives the responses of that filter at every spatial position. So intuitively, the network will learn filters that activate when they see some type of visual feature, such as an edge of some orientation or a blotch of some color on the first layer, or eventually entire honeycombs or wheel-like patterns on higher levels or layers of the network. Now we will have an entire set of filters in each convolutional layer, and each of them will produce a separate two-dimensional activation map. We will stack these activation maps along the depth dimension and produce the output volume. In this diagram towards the bottom, you see some of these different activation maps. So these are two-dimensional, and then they are stacked to give us the depth that we saw in that original diagram of our convolutional neural network. So each of these activation maps have a height and a width, so there's our two dimensions, and once they're stacked, then we get our depth as well. So these are the learnable filters, and these are really what have people so excited, because you can see that each of them are starting to learn how to extract different features. In the bottom, the leftmost image is going to be our first layer of activation maps, and then as we go farther up, we can start to learn more complicated and more detailed structures. So on the far right, you see some pretty cool images that these filters, or these learnable filters, are extracting. So these kind of higher order image representations are what have people debating about the thinking capabilities and learning capabilities of deep learning networks. These are really awesome, and this is actually kind of what your brain does as well. You're going to have specific areas or parts of your brain extracting different features, such as contours, different parts doing color, and then you're going to combine them together to get an overall understanding of the image that you're looking at. And that's exactly what these deep convolutional neural networks are doing. So these representations, very cool. They are the subject matter of a lot of the current research in machine learning. And that's really why we are having this video on convolutional neural networks, because they are at the forefront of what people are trying to do today. And oftentimes, especially for image classification tasks, they are the best. So you're going to want to be able to use convolutional neural networks, or at least know about convolutional neural networks, if you're doing anything with image processing. But let's keep going and explaining these networks a little bit further. And to do that, we are going to use this wonderful video. So let me see if I can get this playing. Yep, here we go. So this is showing how a filter would be convolved or slide across the original input at each layer, because we have a depth of 3. This is an RGB image, or BGR, 3 color channels. And it's going to, at each step, take a stride of what's called 2, and stride is how much our filter is going to move at each step. So you see in this one, if we play it again, it moves 2 pixels every single time the filter moves. We have 2 filters here. They're both 3 by 3 by 3, and you notice again that the filters extend for the full depth of the input. And that's going to produce an output volume of 3 by 3 by 2. Since we have 2 of the filters, that's why we're going to end up with a depth of 2. Notice as well that each individual filter has its own bias unit. So again, we are introducing bias for each filter. And so with this, we have a couple of different hyperparameters. The first one being stride, which I mentioned, and this is how much the filter moves for each step. Typically, this is going to be 1 or 2, 3 or more is going to be very uncommon. And because of that, it's actually going to downsample the input. When we take a stride of greater than 1, we actually shrink the input volume, and that's exactly what you're seeing in this demonstration. So a stride of 3 or more would do that drastically, and we could lose a lot of critical information, and that's why we wouldn't want to generally use a stride larger than 1 or 2. The next hyperparameter that we have is zero padding. And this is simply adding zeros to the outside of our image, because sometimes it will be convenient to pad the input volume because it is a very nice feature that allows us to control the spatial size of the output volumes. Most commonly, we'll see that it is used to exactly preserve the spatial size of the input volume so that the input and output width and height are the same. We're not doing that in this case because we have a stride of 2, but what it is able to do is make it so that the filter can nicely and evenly fit across the height and the width of our image. So you'll see zero padding to varying degrees. Here we're just having a zero padding of 1. 2 or 3 are also fairly common, but you generally won't need much larger than that, depending on the size of your filter. Generally, smaller filters and more of them are going to be a better idea than large filters. So let's take a look at some of the common layers that we're going to run into when we're designing convolutional neural networks. The first, this is what we've been talking about, simply the convolutional layer. Local connectivity, shared weights, learnable filters. But you're also going to see what's called a pooling layer. And a pooling layer is going to progressively reduce the spatial size of the representation to reduce the number of parameters and computation in the network. This is going to be very helpful because it will prevent overfitting, improve our generalization. And the most common form is a pooling layer with the filters of size 2 by 2 applied with a stride of 2, which downsamples every depth slice in the input by 2 along both width and height, discarding 75% of the activations. It's much more beneficial to downsample in these pooling layers than simply using a larger slide in the convolutional layer and downsampling that way. So if you want to decrease the spatial dimensions, you're going to use a pooling layer to do that. Another layer that you might see is the fully connected layer. In fact, you will see, because this is going to occur in pretty much every single network. And the fully connected layer is simply the neural network layer that we've been looking at throughout the entirety of this unit. So neurons in this layer have full connections to all activations in the previous layer, as seen in regular neural networks. You're going to see fully connected layers towards the end of your convolutional neural networks. Another layer that you might see is the ReLU layer, and this is actually just the rectifier activation function explicitly written as a layer. And it's going to apply element-wise nonlinearity. So typically the activation functions in the past have been built into our neurons. In this case, it's going to be explicitly written as another layer. So the rectifier is the most popular activation function for deep neural networks and convolutional networks. So you're going to see it almost explicitly over the sigmoid activation function. And a unit employing the rectifier is called the rectified linear unit. Thus we have the ReLU. So a typical layer pattern might look a little bit like this. We're going to have an input, and then we are going to do a certain number of convolutional layers with our rectifier to apply nonlinearity. And some of those could be followed with an optional pooling layer. And finally, at the end, we're going to get fully connected layers, again, with our activation functions to produce our final output. So this is a little confusing because it has N's and M's and question marks, but this is just the general pattern. Here's an example of what that might look like. So we have an input. It is followed by a convolutional layer with our activations, and then is downsampled with a pooling layer. And this is repeated twice before it goes into a fully connected layer, which has our activation functions. And then finally, that last fully connected is really just going to be your output vector or output image, or whatever your output is going to be for your classification task. So that pretty much brings us to the end of convolutional neural networks. This was just a very brief introduction. You can study convolutional neural networks for the next 50 years and there would be still more to learn. Computer vision tasks are very difficult, but CNNs are starting to make a lot of progress and be able to solve a lot of those problems. So if you're doing image processing, this is certainly the type of machine learning that you're going to want to dive into. And this actually brings us to the end of Unit 4 on neural networks. We are actually going to have a project where hopefully we'll be able to apply and use one of these CNNs, so you'll be able to look at the layers a little bit more explicitly and how it works in Python. And once again, there will be a quiz. So do those so that we can reinforce the topics that we've been talking about and really gain an understanding of these concepts and be able to apply them. Thanks for listening to this unit.